Okay, so here we are with the last example for, maybe it's going to be last example this semester, but also it's going to be last example for the week 9. So in this example, we have a uniform pool that has a mass of 15 kilograms and falls from the rest when the theta was 90 degree. That means it was upright. And told it's going to strike the edge at point A when the theta is going to be equal to 60 degree. If the pool then begins to pivot about this point or the point A after the contact, then what will be the pool angular velocity or the omega after the impact. Assume that the pool does not slip at the point B as it's going to be fall until it's going to strike at the point A. So just let me get the pen here to describe what's happening. So first it was vertical position. Then that's the center point, of course, going to be in the middle at 1.5 distance. So you can see that this was the original point. That will be the second height. Between that, we are going to have change in the height. And that will help me actually to calculate the potential energy for the pool. At the same time, at the beginning, the velocity at the point G was equal to 0. And then we are going to have another velocity G here, and we can find the omega of the bar at this position. So start with the omega to be equal to 0, and then it's going to have another omega, which is going to be the omega 2. During its movement, the angle passed to be 30 degree because it started from upright, which was the angle of theta to be 90, until the theta to be 60. So that's easy to find the change in the height. Okay, so it was 0, then it's going to be dropped down by the value of 1.5, which is the original height, minus this small distance, which is 1.5 minus the 1.5 cosine of 30 degree. How we got that? We make a triangle here. This length is 1.5, so the height is going to be 1.5 multiplied by the cosine of 30 degree. Okay, to take it to that height. So that's what we're going to solve for. And obviously, I'm going to have first fall of the pole, and this will be making the calculation for the conservation energy, and then we're going to have the calculation for the edges we are going to find. So first, that will be the solution in general. That's actually a good free-body diagram. It's very nice, show you all the reaction forces, the height, the position of the G points, and the reaction at the point A, where it's going to be hit the curve at this point, and the rotation is going to be around that point. All the dimensions already being given because we can see them actually from here. We can find the location of the A because we have this is 1.5. We know this angle is 60 degree, so I can find the height, I can find the length of BA. Okay, and that's actually what has been done for this free body diagram. The same way I can find the distance between the G and the A by subtracting that value from 1.5. So we start first by making the calculation, the equation of the T1 plus the V1 equal to T2 plus the V2. Of course, we know how to calculate the T and the V. We will find that the omega 2 is going to be equal to 1.146 radian per second. Definitely this value will be equal to 0 because the omega 1 was equal to 0. And then we can calculate for the I omega 2, which is going to be the value for the T2 in addition to the other stuff. Of course, we can find the value for the omega 2. Therefore, we can find the velocity of the point G, which is going to be equal to 1.27. How did we find that? Definitely, we're going to have the omega for the bar, okay, and we have the velocity at this point. The velocity is going to be equal to the omega multiplied by the r. That's it. The r is 1.5. Then second part is going to be the conservation of the momentum, which is going to be about when it is going to be rotated around the point A. To do that, we're going to simply using the equation that the HA2 is equal to HA3. And from that, we know the value for the omega 2. We only need to find the value for the omega velocity 3. And then we can find the velocity 3. Then we can find the omega 3 accordingly. Okay, so we're going to go through the steps. First, we need to define the three different states of the bar. So the three states we have, first one is going to be when the pole of initial position where theta is equal 90 degree. Then it's going to start to rotate around the point B from state 1 to the state 2. State 2, immediately just before the pole going to strike the edge where the theta become as 60 degree. This third stage or third state is where immediately after the pole will strike the edge at the point A. So it's going to start to rotate around the point A. So the free body diagram is going to be first state to second state is just rotating around the point B, and the G will be dropped down. The weight is showing downward, and we know the I of the bar, and we can calculate, knowing that the omega 1 is 0, so we can find the omega 2. For the state 2 to state 3, first is rotating with the Ig omega 2 with the mass multiplied by the velocity g2, and then suddenly is going to hit the curve at the point A. So we're going to have the force A perpendicular to that point, and we have the two reaction forces at the point B. We have the weight going downward, and this will help me actually to find the third state, which is going to be the Ig omega 3. And here we're going to have the mass multiplied by the velocity 3. Okay, so that will be what we are going to solve for. Now let's collect the knowns and the unknowns. The unknowns is that the mass is 15 kilograms. Also, we know that the velocity of the point G1 is equal to 0 and the omega 1 is equal to 0. The y1 is 0, the y2 is going to be negative of 1.5 minus 1.5 cosine of 30, and this will be equal to minus 0.2 meters. The unknown is going to be the omega 3. To find the omega 3, I need to find the omega 2. So between state 1 and state 2, we're going to use only conservative forces. Does it work? Well, it's going to be the weight. So the T1 plus the V1 is equal to the T2 plus the V2. You remember that the T is equal to half of the IB omega square. Okay, and that means that the T1 definitely will be equal to 0 because the omega 1 is equal to 0. And the T2 is going to be equal to the half of the IB multiplied by the omega 2 square. We can say that this one is going to be equal to 0 because it's going to be the weight multiplied by the y1, which is 0, and this one is going to be equal to the weight multiplied by the y2, which was negative 0.2 meters. Okay, so this one is a negative value. So now we can say that the T2 is equal to the V2, and only the omega 2 is unknown, so we can solve for the omega 2. Later, we're going to come to the second state when we're going to comparing between the impact of the force Fa. All the forces are going to be non-impulsive. So the HA state 2 is equal to the HA state 3. Let's start with the state 1 to 2. So this is the equation for the T. And we solve for the T1. Definitely is going to be equal to 0 because the omega 1 is equal to 0. The state 2 is going to be omega 2, which is unknown. So from here, the IB, of course, is going to be equal to 1 over 12 multiplied by the length multiplied by the, length square multiplied by the mass. And by substituting that in the equation, it's rotating around the point B, so it's going to be 1 over 3. Okay, and from there, we can find that the value in terms of the omega 2 square. The V1 is equal to the weight multiplied by the Y1, which is 0, so it's going to be 0. For the second case, it's going to be the weight multiplied by the Y2, which is negative 0.2. And we're going to have the value in total. So now we can say that the T2 is equal to the V2. From there, we can find that the omega 2 is equal to 1.146 meters per second. By that, I can multiply the omega 2 by the distance from B to G, which is 1.5, and I can find that the velocity at the point G in the second state is going to be equal to 1.72 meter per second. Done. We did now half of the solution. Now let's go to the second state, where we're going to have the that the bar is going to hit the curve at the point A. So in that case, the Ig is going to be 1 over 12 ml square, and the HA equation is the Ig omega plus the mass multiplied by the VG RGA. Okay, so that's the general equation. So for the state 2 and for state 3, we can write down the equation as following. You can see that in the HA3 state, we have the omega 3 is unknown. Of course, the VG3 is also unknown, but we can say that this value is going to be equal to the omega 3 multiplied by the R multiplied by the R again. And then we're going to find the whole equation to be in terms of the omega 3. And for the HA2, we know the Ig now, we know the omega 2, we know the velocity G2, we know the RGA, so we can solve for that. And it's going to be equal to, it should be equal to a value. I hadn't calculated that one yet. Anyway, so here we substitute the VG3 by the omega 3 multiplied by the RGA. And thus we're going to find the value for the second side of the HA3 to be equal to the Ig multiplied by the omega 3 plus the 15 multiplied by the RGA square multiplied by omega 3. So we can find the whole H3 as terms of the omega 3. Now everything can be substituted in, and we know that the HA2 is equal to the HA3, and thus we can solve for the omega 3 to be equal to 1.53 radian per second. Okay, so that's it. You can see that once again, it looks like a very complicated question, but the answer is quite easy if we focus on how to do it. Okay, thank you very much, and see you.